I'm going to give some examples of what we've achieved with our XRF since we got it just under a year ago. I'd also like to thank Paul Lansdale, who's in the audience today, for providing funding for this system and believing that it would do what we said it was going to do. I'm going to start with a quick background to what our expectations are of the system. The two main things that we wanted to achieve with the system was we wanted to be able to see the chemical distribution on the macro scale on samples that we've been told are homogeneous for quite a few years, but haven't necessarily believed that. And the other thing that we've been trying to do is we have a casting facility at WMG, and we wanted to use the Micro-XRF to see how homogeneous the things that we were producing in that casting facility are. So we bought our M4 Tornado last year. It arrived in January, and like I said, one of the primary things we were trying to do is look at the segregation characteristics of castings, but applied to other systems as well. So we wanted something that was versatile. The most important thing that we wanted to achieve was we wanted to reliably map the chemical distribution on the macro scale. Reliable quantification is nice too, but the most important thing was we wanted to see how things were distributed. We haven't been that adventurous with our settings. Our typical parameters are given there. We tend to run a lot of things with that filter, and the reason we use that filter is we don't like diffraction stuff getting into our maps, because if diffraction gets into our maps, we can't see how things are distributed reliably. So we're very keen to get rid of diffraction effects. But we're always keen to learn, and we always want to increase our sensitivity, because when we're putting these filters in, we sometimes worry that we're reducing our sensitivity. We want to improve our quantification reliability, and we always want to do things faster. Why did we buy the XRF? Well, when we bought a lot of our other systems, we were very keen to be very good at doing chemical distribution at different length scales. So starting at the TM, where we've got a genuine capability of looking at chemistry of atomic level chemistry. Then moving down to our SEM, where we can reliably map things at the hundreds of nanometer range over maybe millimeter length scales. And then in between we've got our FIB, which has a Hyde Sims, which can do very light element, for example, lithium detection. So we felt that we had a full, within our microscopes, a very strong analytical capability, but we thought the XRF, Micro-XRF, would extend that chemical mapping into the kind of more macro scale. And this is also complementary to other chemical techniques that we've got at the university. For example, we've got Dave and Steve there from our central facility, who have an XRF which can do just bulk, but across the whole element spectrum. And we've also got things like OES, which again are complementary techniques. So this slide just introduces our casting facility at WMG. We bought a VIM, I think 2 or 3 years ago now, and that can cast ingots up to 10 kilograms. We bought an OES to be able to just sanitize what we were putting in and what we got out, but we were very keen to look at the segregation characteristics of the castings that we produced as well. And this slide just shows a typical example of something that we cast and then later analysed to see the segregation behaviour. And as you can see, there's a secondary dendrite arm spacing changes through the thickness, indicating a change in cooling rate. And from this data, so this data was obtained from Carl, he then uses this segregation characteristic to input into finite element models, and that gives local solid solution strengthening information, and it can predict differences in local strain. We also do quite a lot of work on superalloys, and superalloys are very chemically complex. They have typically a lot of elements in there, and when we do our analysis on these, we often assume that they're homogeneous, and that assumption, as you can see from these XRF maps, isn't necessarily so good. So I can't tell you what alloy this is, but it's a typical single crystal superalloy. We can then, for example, on the rhenium, where we see the very clear dendritic structure, we can then quantify across these dendritic arms the rhenium content. This data is statistically good, so we can see that the variation in rhenium content varies between 3.5 to 5.5 weight%. And what this can do is it can allow us to target specific regions in a sample in more detail. So if we're going to do focused iron beam or SEM, it's very important to understand the bulk chemical distribution before we start looking at local areas. The next example I'd like to show is some work that we did on a dissimilar metal weld, or DMW. We got these samples from the Electric Power Research Institute in America, and the question they asked me is, what's the composition of the weld metal? Okay, so what we would do if we didn't have Micro-XRF is we'd stick it in an SEM, and we would do chemical analysis in maybe 10 regions and take an average. But when you look at the length scales over which the chemical composition changes in this sample, that would not be an adequate solution, because you can see that all these different weld beads have different compositions. And we can do that, we can have a little look at that in more detail here, where we can, from the map, derive compositions from different regions, and we can also derive an average composition of the weld metal and compare it with the parent as well, which is shown in object 1. And what this data shows us is that if we're getting a variation, for example, in iron within the weld metal from between 7% and 50%. So without Micro-XRF, you just simply wouldn't be able to answer the question, what is the composition of weld metal, accurately. We're also interested in how the quantification we got from the XRF would correlate to what we're more used to in the SEM. So based on this map showing the compositions in XRF, we were then able to go into these areas and do EDS in the SEM just to get sanity on how close we were with the techniques. And what we see is that we were very happy with how close we were in all the areas we analysed. Obviously, with the caveat that Micro-XRF doesn't tend to perform brilliantly at the light element range. One of the things we noticed on the work on the DMW is we're actually seeing segregation in the parent alloys as well. So what we wanted to do was look at that in more detail on a parent steel, and this is an example of that here. And this is some work that was done by Shahid. So this is a 9 chrome power plant steel. One of the things we're working on this project is trying to work out areas which are most prone to creep damage. So being able to get a chemical map showing variations in composition, that helps us to look at which areas are most likely to be affected by the damage. And as we can see here, there's significant molybdenum segregation in these flow lines. We can quantify the compositional change within these lines just from the map data, and then we can go into an SEM and try and find the same segregation behaviour in an EDS map and an SEM. And we found this really difficult, even when we were collecting under very aggressive conditions, 150,000 counts per second for 10 hours, we can only just about see the segregation lines in an EDS map. And I think that's because the sensitivity of XRF is higher when you think about how you're averaging a larger volume with each pixel, whereas in the SEM you get a lot more noise because you're looking at small features. And why is that important? One of the things we're trying to do on this project is we're trying to quantify microstructural features. For example, here we're trying to quantify second phase particles. And if we compare an area where we've got the lower molybdenum content with an area with a higher molybdenum content, there's a 30% difference. Also, the segregation characteristics of elements like molybdenum will also follow with segregation of more tramp elements as well. So it helps us know where to look for certain types of features. So just to summarise, Micro-XRF is an important technique for us to quantitatively map sample homogeneity. This is important as it helps define where to undertake more detailed microstructural characterisation work, and it is also an important tool for us in terms of segregation within cast alloys.